having described the mechanism via which convection occurs inside of systems that are colloquially described as external flows, as an object that is transferring heat to some semi-infinite fluid that's surrounding it, having figured out what the workflow for discovering heat transfer rates and heat transfer coefficients in such systems is. Now that we know that workflow, it makes sense to start establishing that workflow for another class of system where convection and understanding convection is super important, which are the so-called internal flows. And true to the name, the whole idea of internal flows is that the liquid is no longer surrounding the object, it is now contained by the object. And so you can imagine that this is a super important class of system to study simply because of the fact that, pipes, which are a key component of every HVAC system and every central heating or cooling system in every building that you can think of, that studying how heat transfer occurs inside of pipes or ducts is important for understanding how heat transfer occurs inside of the standard HVAC systems. And in particular, we have to set up the appropriate variables and the equations and things like that that will let us figure out what the behavior of these systems is, okay? At least from the perspective of heat transfer. So here's a kind of standard setup for these sorts of systems. We have some sort of duct. That duct has a diameter d. Now I've drawn it as a circle, but we'll see that it doesn't actually have to be a circle. This could be a square duct or a triangular duct. But for the moment, just consider a circular duct with a diameter dh and some length L, okay? And liquid comes in with some specific heat capacity and dynamic viscosity, thermal conductivity, and mass density. It comes in at some temperature Tmi, which we take as being kind of a averaged cross-sectional temperature of the liquid at the inlet, and then exits this duct at a temperature Tmo. The I and the O, by the way, are symbols that I'm using to represent inlet and outlet, okay? That liquid comes in at some kind of representative velocity um, or speed um. We're going to talk about what that velocity is in a second. But the whole idea is that as far as the physical setup goes, this is really just a liquid flowing through a tube, right? A duct, a generalized tube. And that as it flows through this tube, heat transfer occurs between the surface of this tube, which maybe is at a uniform surface temperature Ts, or maybe it's not, such that there is some kind of heat flux everywhere along this tube surface that is transferring heat from the tube to the liquid. In the case of heating, if it was cooling down, then you can imagine that it's moving backwards. For the purposes of what we're going to talk about now, I'm just going to assume that the heat transfer is happening into the liquid, but obviously you know that that's just a sign convention, right? If the values you get are negative, then it's just heat fluxes and heat transfer that's going outwards. Okay. So this is the kind of general setup. We don't demand that the duct be circular. Just makes life easier because one, the calculations are simpler, and two, pipes usually tend to come in circles. But the one thing that we will demand is that the cross section is constant. That is to say that this thing doesn't transform from like a circle to a triangle, or that the circle doesn't suddenly start to widen. Okay? And so obviously there are a lot of systems where that sort of thing matters, but that's not the sort of thing that we want to consider for this analysis. Okay? And if we are dealing with a cross section that is not circular, right? So if this is not actually a pipe, then we can define this diameter, which we are now going to call a hydraulic diameter, because it's some kind of like effective diameter that we can use to represent the geometry of this system. When we do, when we actually start to establish our workflow, we can define this hydraulic diameter as being 4 times the cross-sectional area of, the duct divided by its perimeter. Okay, so just to give you a sense, right, this object has a cross-sectional area. It also has a perimeter, and so we define the hydraulic diameter by taking this ratio. In the case where this is actually a circle, you'll find that this equation comes down to just the standard equation for a diameter. Okay, so this evaluates to the actual diameter when the cross-section is a circle, which is, of course, kind of, I guess, an expected consequence of this kind of definition. But be aware, right, that this accommodates any kind of cross-section. The goofier the geometry, mind you, the less the correlations in the workflow will stand up to scrutiny, right? The more errors you're going to get because all kinds of weird stuff starts to happen when the geometry is more complex. But at the level of the analysis that we're trying to do here, this is fine. So remember that this perimeter is important. It'll show up in the calculations that we do a little bit later too. Anyways, we have this setup and we are interested, for example, in trying to figure out, well, what is Q? Like, what's the heat transfer rate that's happening to the liquid? If we take all of these heat fluxes and we integrate them up, of course, we get a heat transfer rate. What is that heat transfer rate? Okay. And perhaps unsurprisingly, it'll have to do with what these two temperatures are. But the way that we actually get that dependence is going to be something that is maybe not something that we've seen in detail before. We have talked about it briefly. We talked about it when we discussed the problem of convection, but it's not something we ever spent the time like doing the math on analyzing. Because, right, if we assume that the only heat transfer that's occurring in the system, the only movement of thermal energy that's happening is from the surface of the pipe down into the liquid in the pipe, well, we have all of this energy going in. Where is it going out? Right? If we assume that there's no heat transfer happening through the pipe, like in this direction, and that everything's happening in this direction, and we further assume that the liquid is not generating heat, that there isn't some kind of chemical reaction that causes it to generate heat, and that the temperatures that we're describing here are steady, right? That nothing in this problem changes over time, at least not from the perspective of what we've drawn. If this is the case, trying to set up an equation that balances the energy rates inside of the system will tell me that the net heat transfer going in through the pipe is 0, which doesn't really make sense. Right? Clearly heating or cooling is going on. This temperature is going up from TMI to TMO. So how do we account for it? Well, remember, every little chunk of liquid has thermal energy, all right? If I have an object that has some temperature T and some mass M and whatever, or volume V, we had determined that we can approximate or at least model the thermal energy of that little chunk of matter as being the following. We had said that this was roughly equal to rho times Cp times the volume times the temperature, right? We had said that this is how we model thermal energy in things that have mass, at least for the purposes of this course. If liquid is flowing into this system with a temperature TMI and leaves the system with temperature TMO, that means that the liquid must have absorbed some thermal energy, right? Because the thermal energy that we're writing down here has increased. There had to have been a heat transfer process that caused the thermal energy of this liquid to go up. And so as a result, what we really find is that, remember, whenever we do an energy balance, what we're really doing is we're describing a region of space. And we're trying to understand how energies change in that region of space. And in this region of space, we have this flow of matter with this thermal energy that enters the geometry and by extension represents an inflow of thermal energy. The difference between this and what we had talked about before is that inflow of thermal energy is now not happening as a result of a temperature difference. That inflow of thermal energy is happening because that matter with thermal energy has a velocity and is moving inwards, okay, into the system. And by extension, we have matter that is at a temperature TMO that leaves this system as well. once again because the matter has speed and therefore moves and takes its thermal energy with it. And so it turns out that we can't just consider the thermal energy transfers that are occurring in this region of space that happen because of temperature imbalances. We have this other mechanism, which is usually called the thermal advection, this other mechanism of moving energy in or out of this region, of this control volume. And now, in order to be able to account for that in our equations, well, how do we try to write this down? I mean, if this matter has this thermal energy, like how do we account? Well, the density of the object doesn't change. The specific heat capacity of the object doesn't change. The temperature, of course, will from inlet to outlet, but it won't change at the inlet or at the outlet. We're assuming, for the purposes of this analysis, that the temperature of the liquid is roughly uniform, is roughly TMI or TMO, and that using this, right, we can model the system. The thing that is changing is how much is going in, and we quantify that by creating this thing called a volumetric flow rate, okay, which is just the rate of how much volume of fluid goes into this region, or out, I suppose, per time, okay? So this V dot is a volumetric flow rate, and it has units of volume per time. And the international system, meters cubed per second, okay? Most of the time, what people prefer to do is that they take this volumetric flow rate and they combine it up with the density. And so they say there's this thing called a mass flow rate, which has units of kilogram per second in the international system, or mass per time, which is really just the density times the volumetric flow rate, okay? And so this, pardon me, just got to make sure I put the dot there. This expression tells us how much the thermal energy of this region, how much flows in, or the rate at which it flows in, as a function of things that we can try to figure out, right? We can try to figure out what the mass density is. We can try to figure out the specific heat capacity. We can try to figure out the temperatures, the inlet or the outlet. But we could also try to figure out what this volumetric flow rate is, or by extension, what the mass flow rate is. And how do we define these quantities in terms of this sort of characteristic speed that we had attempted to create at the start of this lecture? Well, relatively simple. It's pure geometry. The whole idea is that this UM over here, we can define it as being the volumetric flow rate divided by the cross-sectional area, right? And you'll see, right, that if you check the units for this, hopefully it's intuitive already, but if you check the units for this, we have something that has units of volume per second. You divide it by an area, and now you have units of speed, meter per second. And so this is how we define it. And then, of course, right, if we wanted to get what this characteristic speed was as a function of the mass flow rate, then we would simply multiply by the density on the numerator and the denominator of this thing. And then all we would get is just an m dot divided by a rho times AC. So, simple enough. And I'm going to rewrite this expression over here using the m dots simply because that usually is how it's most commonly represented in the literature of heat transfer. So this is just m dot dp t. Okay. So given that we have this understanding of how much energy goes in or out of the system, we can now derive an equation that tells us how much energy, or the rate at which energy is being transferred into this tube, right, into this liquid. The whole idea is basically to say, well, if we integrate all of these heat fluxes, then that's going to give me my heat transfer rate going in. So when it comes to writing down the equation that we've always been writing down, when it comes to doing energy balances, right? This isn't going to change because the system is in steady state. It's 0. There's no thermal energy generation, so that goes to 0 too. And now the real question is what's going in and what's going out. The integral of all of this heat, of all of these heat fluxes, the net Q, at least the net Q that we're considering, is going inwards, at least based on the diagram. So E dot in is equal to Q. But then notice that we also have a contribution that's coming from the inflow of matter with thermal energy at the inlet, which is just plus m dot Cp Tmi. All right? When it comes to the energy outwards, right, the energy that's leaving the system, well, we have the outflow of energy in the outlet, which is just m dot Cp Tmo. So now that we have these two calculations, of course, we know that this minus this has to be equal to 0. And setting that equation up gives us what I like to call the golden rule of internal flow. And I call it the golden rule because it is so simple and so easy to use for these sorts of problems that you never want to forget that it's useful for basically everything, which is just to say that Q, the total heat transfer rate that's occurring through, the edges of this pipe into the fluid, is just equal to m dot Cp times Tmo minus Tmi. Right? So the difference in the thermal energy rate, I guess you could say, at the inlet and the outlet gives us the heat transfer rate that has to be happening off the sides. And so it's very, very simple because you can now immediately figure out what the heat transfer rate is through a system like this, as long as you know the inlet and outlet temperatures in the system, and of course the material properties. As long as you know these things, you can figure out heat transfer rates from temperature differences or vice versa, which is very convenient. Now, we have an understanding of how we can calculate the heat transfer rate, but we also have to consider the following, right? The temperature of the liquid is not the same everywhere. And now we had approximated, or we will approximate, that at every kind of location, at every cross-section that we take of this pipe, we're going to say, oh, the temperature of the liquid is roughly Tm, okay? But that Tm changes, or potentially changes. Well, I shouldn't even say potentially. It obviously changes because it has to go from Tmi to Tmo. That's kind of the whole point. And so it makes sense for us to try to understand how that temperature changes from Tmi to Tmo, and whether or not that depends on the way that we heat up the system. In particular, there are two different cases that I want to consider. The first case that I want to consider is what happens when I have a uniform heat flux. So I set up a toaster or whatever on the surface of this pipe, and I fix the heat flux at the surface of this pipe to be a specific number. Okay? Another thing that I can do is I can maybe set up a thermostat. I have some liquid or something else, some machine that is keeping the surface temperature of this pipe at a fixed number Ts. And then based off of that, we can ask ourselves, how does the temperature of the liquid change as we go from the inlet to the outlet? All right? So to do that, the first thing we should do is define a little coordinate x that, is equal to 0 at the inlet and grows to the outlet, and try to see if we can't generate some kind of energy balance or simplified energy balance that will tell us an equation that governs that temperature change. Okay? So what is that equation? Well, let's try to do just like we did before an energy balance, but this time we're not going to do it over the whole pipe system. We are going to do it over a little sliver right here. It doesn't actually matter where exactly we do it. The whole point is that we have a, let's say, TM1 on one side, and we have a TM2 on the other, and we have that this thing has some thickness delta X, okay? And let's try to see if we can't understand what, the balance of energies is in this. And the answer is that this is going to be extraordinarily similar to what we had seen before. The only difference is that we're eventually going to contract this thing into a tiny little, an infinitesimally tiny sliver. So just like before, the whole idea is supposed to be that we have that Q is equal to m dot times Cp times Tm2, right? Temperature at the fake outlet, minus Tm1, the temperature at this fake inlet. This Q is really just the integral of this heat flux over this little, chunk of curved surface area that surrounds the liquid over the pipe. And this works, right? This is the exact same kind of equation that we had seen when we derived that golden rule for the whole pipe. But the idea is that now we can try to see what happens if we shrink this further and further. And if we do, if we try to attempt to shrink this, this integral, that Q, can be approximated, roughly speaking, as being a constant Q double prime, right? Because as we start shrinking this, right, variations in X go down. And so the Q double prime is not going to vary that much as we move from the fake inlet to the fake outlet. And so we can approximate the total Q as just the multiplication of that Q double prime times the perimeter of the duct, or the perimeter of the cross-sectional area of the duct, the perimeter of the cross-section of the duct, pardon me, times this thickness, delta X. And the nice thing about this is that we can then take this delta X over here and pass it to the other side. There we go. And what you'll notice occurs is that if we take this delta X to be smaller and smaller, this term right here starts to look like a derivative of the mean fluid temperature, the average fluid temperature at a given cross-section, which then gives us a differential equation, which is what we were fishing for, right? Now what we eventually find, try to see if I can write it a little less crooked this time, but no promises. We find that dTm dx is equal to Q double prime times P divided by m dot Cp. Okay, so the rate of change in space of this fluid temperature is equal to the heat flux at that specific location multiplied by the perimeter of the cross-section divided by the mass flow rate times the specific heat capacity. Neat. Now, consider the situation where the heat flux is uniform. Okay? If the heat flux on this pipe is uniform, then this Q double prime is just a single number. Okay? And if it's just a single number, right, the perimeter doesn't change by construction, the mass flow rate doesn't change by construction, and the specific heat capacity doesn't change by construction. And so as a result, we find that this is just the rate of change of Tm with respect to X, that is a constant. And so therefore, the temperature variation is going to be linear for Tm. Okay? And so we find that whenever we have a situation where there's a uniform heat flux that's being imposed onto, a duct that is carrying liquid, whenever we have that uniform heat flux, we find that the temperature of the liquid is going to increase linearly, okay, as a function of x, with a, governing constant given by this, okay? Obviously proportional to how large that heat flux is, but also the perimeter of the duct and mass flow rate and the specific heat capacity. And so, wonderful. Now what happens if we have a constant surface temperature? Right? So what if instead of having a constant heat flux, now we have a constant surface temperature over the pipe? Well, this now becomes tricky, because now we have to rely on some kind of model that tells us how heat is being transferred between the surface of this pipe down to the fluid. Right? Before it didn't matter because we just assumed that we had the number for the Q double prime. And the model that we use to describe heat transfer between a solid, right, the surface of the cylinder, and the actual liquid is the convective model, the model of heat transfer between different objects. And that model is just that Q double prime is equal to H times the surface temperature of the pipe minus the fluid temperature. Okay? And this brings with it some complications, because now, right, we're introducing another temperature into the mix, which is the surface temperature of the pipe. But we also have to consider heat transfer coefficients, right? Now we actually have to think about the process via which we find a heat transfer coefficient. Now, there's one thing that I'm going to tell you about heat transfer coefficients inside of these systems before we continue any further that will make our lives considerably easier and will explain what the correlations look like when we actually start doing the process of figuring out the workflow for internal flows. And it's the following. Whenever we consider flow that's occurring through ducts, we always kind of assume that there's this uniform flow right at the start and then changes the moment it goes in. And so how does that flow change? Well, remember that the no-slip condition, the same no-slip condition that we considered applied for flow past flat plates, applies, say at this little chunk of pipe inlet. If we zoom in, hard enough, you can imagine that the curvature of this thing kind of goes away. And so from the perspective, at least the microscopic perspective of the fluid, this thing is just like a little tiny flat plate. The no-slip condition applies, and so of course, in this little strip of not quite flat plate, we expect to see a boundary layer form, right? A region from which the speed of the fluid goes from 0 all the way up to some number. We don't necessarily have the tools to figure out what that number is, nor do we want to find it in the context of a course on heat transfer. But the point is that the flow inside of this thing is not uniform, okay, right? This UM is just a representative speed that tells us not necessarily an average, but something close to an average between speed 0 at the boundary of the pipe and whatever that maximum speed is. And the thing is that, of course, this boundary layer, just like in flat plates, starts to grow as we go further and further in to the pipe system. But that boundary layer is also forming on the top end too, and on the sides, right? And it's a duct, so of course it would. And eventually what happens is that because this liquid is no longer semi-infinite, those boundary layers collide. And so the notion of a boundary layer kind of goes away, because now there isn't a specific region in space over which the fluid the fluid characteristics are changing and over which they're not changing, right? At some point, those boundary layers collide, and therefore there isn't really a good definition of what a boundary layer is. The entire flow is boundary layer, so to speak. And so we call the region before, from the inlet all the way up to the point where this occurs, we call this like the entrance region, which usually for practical systems tends to be pretty small. And then after that entrance region concludes, we make an assumption that the flow after the entrance region all the way up to the outlet is called fully developed. And what that really means is just that the characteristics of the flow are not going to change from here to here to here. All right? They're going to be independent of x past the entrance length. Now, we have to be a bit careful about this because when we consider turbulent flow inside of pipes, turbulent flow is chaotic, it's unsteady, it moves around in unpredictable ways. So certainly you can expect that the flow here is not going to be the same as the flow here in a turbulent flow. But on average, the characteristics that you find, the average speed, the average heat transfer rates, the average heat transfer coefficient, all of those things do remain the same. So from the perspective of our calculations, which for turbulence, of course, has to be based off of time averages, from our perspective, we are just going to assume that everything is the same, right? And if we make that assumption, if we make the assumption that the flow characteristics are the same everywhere around here, it stands to reason that the heat transfer coefficient that we find is going to be the same, right? How can we justify this? Well, we'll talk a little bit more about it when we actually get to the workflow. But if the characteristics of the flow don't change, and the H is determined uniquely by the characteristics of the flow, then of course the H shouldn't change, right? That the H doesn't vary as a function of X in this fully developed region. There is a complex history of study of what happens here in this entrance region, but we won't touch on it in this course. For the most part, what we're going to assume is that our parameters are such that this entrance region is quite small. Small enough that any alterations to the calculations that we do when it comes to actually establishing the workflow for these problems, any alterations caused by ignoring the entrance region are negligible. Okay? And so this is just an extraordinarily long-winded way of me saying that the H is going to be a constant for all of these problems, but also giving you a sense of, what the characteristics of a flow inside of ducts is. Also, one other thing I should mention. When does turbulence occur inside of internal flows? Here it's actually going to matter. You'll see that it will matter in the next lecture when we actually start doing exercises. But the whole point is that in internal flows, rather than in flow past flat plates, turbulence occurs everywhere once you get past a critical Reynolds number. So before, the whole idea was, it always starts off laminar and flow past flat plates, and then eventually, once you get past a specific distance, the flow will become turbulent. In these scenarios, the idea is that we define a Reynolds number based on the diameter. Okay, so we create a Reynolds number, just like we did for cylindrical systems, and we say, oh, well, this is just rho u infinity d times mu, or I guess pardon me. We create a Reynolds number that looks like this, and then once this number is larger than a specific quantity, then the flow is turbulent everywhere. What is that number? For internal flows, this is a very rough approximation, but usually the critical Reynolds number is considered to be approximately 2,300. That's just what it is. So if your Reynolds number is larger than 2,300, the flow is turbulent everywhere. If it's lower than that, it's laminar everywhere. Okay. Sorry, I got sidetracked there a little bit, providing you some important information about how flows are characterized in these systems. But let's get back to the thing that we're here to do, which is to try to determine how the temperature of the fluid changes as a function of x in a scenario where we have a constant surface temperature. So going back, inserting the convection equation that we had written down for Q double prime into the original equation that we derived for dTdm dx, we get dTm dx is equal to H times Ts minus Tm times P divided by m dot Cp. That's the equation we got. And remember that I wrote down Ts minus Tm because we're modeling the heat fluxes happening into the system, right? We're just trying to be consistent with the notation. So what winds up happening here, interestingly enough, is that we have an ordinary differential equation that relates dTdm dx to Tm. with this extra little constant term coming from the TS. That one's kind of annoying. So why don't we try to get rid of it? Why don't we say that we define some temperature difference, delta T, that delta T I'm going to call TS minus TM. Okay? Doesn't really matter in which direction you define it, whether or not it's TM minus TS or TS minus TM. It won't matter. Ultimately, the equation that you get will be the same. So we can define this temperature difference. And this is very similar to what we had done for lumped capacitance. And we are just going to try to see if we can't relate the time derivative of this temperature difference to the time derivatives of these two things. Or, pardon me, we want to figure out how we relate the spatial derivatives of this delta T to TS minus TM. We had done it for time derivatives in the lumped capacitance case, but nothing here is changing in time. Or at least nothing from our reference frame is changing in time. So if we take the derivative of this thing with respect to dx, or so with respect to x, this isn't going to change because we had established that the temperature of the surface of the pipe is constant everywhere. But this temperature, of course, changes. And so what we find is that the rate of change of this thing with respect to x is the negative of the rate of change of this thing with respect to x. So we can rewrite this equation as the following. Oh, pardon me. We can say, and I'm moving a negative sign from one side to the other. I'm just saying that d delta t dx is now equal to, let me just erase this thing to make it more compact, minus h delta t, the perimeter, divided by m dot dp. And now this is an ordinary differential equation that looks just like the one that we had seen in the lumped capacitance model. The only difference, of course, is that we have an equation where the derivative is in x, not in time. And so if we integrate this, if we try to find an expression for this, well, what do we wind up getting? Well, let's consider that we're going from the inlets all the way up to some specific location x down in the middle. If we do that, what we will wind up getting is just that the difference in temperatures between the surface of the pipe and the fluid as a function of x is equal to that initial difference at the inlet multiplied by an exponential. An exponential, which is just hpx divided by m dot cp. There it is. And so you can imagine that if we wanted to calculate the temperature difference all the way at the outlet, then we would just replace this x with the pipe length L. And so we find here that the temperature differences drop exponentially between the surface of the pipe and the fluid. And of course, you can imagine that because this Ts is a constant, then that really means that the temperature of this liquid goes up and asymptotes all the way up to Ts. So if you make this x larger and larger, eventually what's going to happen is, of course, that the difference in temperatures between the liquid and the pipe surface go to 0. Does this match up with our intuition of how these systems behave? Sure, because consider it, right? We know that the liquid that is in contact with this pipe is going to be leaching heat off of it. And we are not considering that anything is changing over time simply because of the fact that we are in a reference frame where we get to see the liquid flow past us. But if we were in a reference frame where we, are like inside the liquid, this was like a huge, container, and then we have like a little probe that we dunk into it, we would see that the temperature of that little probe starts off at TMI and then increases over time as it flows through the system all the way up to the outlet where it reaches a temperature TMO. And so really the model that we created for lumped capacitance and the model that we're using to create this equation is essentially the same thing. The only difference, of course, is the parameters that we get that govern how quickly or how slowly this process occurs, and also the fact that one of these is occurring in space and the other is occurring in time. But that's really only because of our frame of reference. Okay? So this is the expression that we get. And so in one scenario, we find that the temperature of the fluid increases linearly, right? That it increases whenever, linearly whenever we have a constant heat flux. And then we find that it increases exponentially, but be aware, right? An exponential that asymptotes to a specific number whenever we have this uniform surface temperature, Ts. And so phenomenologically, that is how we describe these sorts of systems. And you can imagine that using either this equation or the differential equation that we saw before, where we just say that, dTm dx is a constant, combined with that golden rule, those three equations, or two equations, I guess, for each different kind of version of the system, will allow us to be able to determine things connected to internal flows, like heat transfer coefficients and heat transfer rates, as a function of everything else in the system. Or even that we can use those heat transfer rates to find outlet or inlet temperatures. The one thing that we haven't described, which I will talk about in the next lecture, is how you try to figure out what the H is. Because even though we've said that the H has to be a constant over the fully developed part of the flow, which we're assuming is everywhere, at least approximating it is everywhere, we don't actually know what those correlations are, and we don't know what the workflow for finding those are. But we will in the next lecture. So one last thing before we start talking about examples. We wanted to figure out different equations that we could use to determine the heat transfer rate through internal flows from a pipe down into the liquid or vice versa. And we had set up this kind of golden rule that allows us to determine what the heat transfer rate through the pipe is as a function of the inlet and outlet, mean fluid temperatures and the mass flow rate and the specific heat capacity. But we can also set up two different equations that allows us to figure out what that heat transfer rate is independent of the mass flow rate associated with the system, focusing only on either information given to us by the constant heat flux or by the temperature of the pipe in a scenario where you have a constant heat flux or a constant surface temperature, respectively. And so the equation for the constant heat flux case is relatively simple. All it is just a geometric kind of restatement of the fact that the heat transfer rate is equal to the heat flux times the surface area over which the heat transfer takes place, which in this case is just this curved surface area, which is the perimeter of the duct times its length, right? However, when we're considering the constant surface temperature case, it turns out that because that temperature profile is exponential, right? Because it's not this nice linear thing, well, it turns out that the right way to state it is by using kind of the same conceptual description that we had come up with before when describing convective heat transfer, the idea that the heat transfer rate is proportional to a heat transfer coefficient multiplied by a surface area, right? The same surface area over which the heat transfer takes place. But now, right, because the difference in temperature between the fluid and the surface is not constant, then we can't really use that temperature difference because it's not the same everywhere. We have to somehow come up with some sort of representative, not quite average, but some representative temperature difference value to use in this equation. And we can get that by taking the equation that we had written down before for the exponential profile, of the temperature difference between the surface and the fluid, right? That delta T is a function of x, and plugging it back in to this kind of golden rule of heat transfer. And what we inevitably find is that in order to make this equation work, an equation that involves a delta T, the temperature difference that we need to use is what's called the log mean temperature difference. And the way that you calculate it is simply by taking the difference in the differences, however confusing that may seem, and then dividing it by a logarithm of delta T0 over delta Ti, where delta T0 is just the difference in the surface temperature and the fluid temperature at the outlet, and delta Ti is the difference in the temperatures between the surface and the fluid at the inlet. Okay? And so you'll notice that this isn't quite an average. This isn't quite a mean temperature, but it can't be, because remember that we don't have a kind of nice, simple, linear dependence on x of the temperature profile of the fluid. It's exponential. And so because it's exponential, it's perhaps no surprise that we wind up getting this kind of logarithmic weighing factor when it comes to calculating this. And so the point of showing you these equations is that we can use any two of these for the specific scenarios that we're dealing with in order to try to calculate heat transfer rates and heat transfer coefficients or temperatures as a function of each other. And each of these equations, this one and either of these in their respective scenarios, will allow us to create a mathematical setup that will allow us to solve for whatever unknowns we have in our problem, which we will see when we work on exercises in the next lecture.